Data compression with respect to Q. Unfortunately, P is true. You're not Shakespeare. Shakespeare, or his twin brother, going through the text, could achieve a data compression of H of P on the true distribution, Shakespeare's distribution P. But U will have a compression not H of P, but H of P plus dPQ. So the relative entropy distance between your distribution on text and Shakespeare's distribution on text is the cost. The excess above the data compression limit, H of P, that you could achieve. All right. And after arithmetic codings, we want to look at something that we can't resist. The best way to code. Not a roof code, which is quite fine, but the best way to code. Something usually strictly better than the roof code. And that's the Huffman coding. And then we probably will come up with some examples if I don't go off on too many tangents. All right. All right, let's prove this theorem first, and then I'll prove the dPQ theorem second, and then we'll go into arithmetic coding, which for some reason well, let's just say one. When I looked over my notes and prepared the notes today, I got more excited about the arithmetic coding than I did about some of the other parts. So, I reveal my bias. Theorem L greater than H sub D of X. We want to prove it. So X is drawn according to P of X. X in script X, the alphabet. And here's the proof. This is the assumption. This is the proof of the theorem. L minus H sub D is the summation of Pi, Li, minus summation of Pi log to the base D of 1 over Pi. All right? This is the entropy term, and this is the L term, the expected length. And we wish to show that this is positive, and therefore the theorem is true. Well, I'm going to write L sub I equals log to the base D of D to the L sub I. Okay? That's an identity. And I'm going to write R sub I equals D to the minus L sub I over the summation of d to the minus lj over all the symbols. And I'm going to write c equals summation d to the minus lj. All right, why have I done this? Well, I'm defining a probability distribution R in terms of the length. So I give you any set of lengths satisfying Kraft's inequality, and I can then say that these lengths are perfect with respect to this distribution. By the way, let's say d is 2, the binary case, then all these probabilities that I get this way will be things like a half or a fourth or an eighth or a 16th or so on. In other words, right. And in those cases, C will be 1 and L will equal H. But, right. Okay, now what? L minus H sub D is equal to summation of pi log to the base d of pi over d to the minus li, because li is log to the d li, and so I just plug those in. This becomes d to the li, and the log of it is li, so that's the pi li term, and the other is the entropy, summation p log p. Now, I normalize this by summation d to the minus lj, which means I have to divide by summation d to the minus lj. So I've turned these into probabilities, but I normalize here, and then I do the identification that I have here, and this becomes log the base d of pi over ri times c. One over c. Alright. And now I have Ri is a legitimate probability distribution, so it's pi. So this is summation p log p over r. So this is dpr plus the expected value of log 1 over c, which is plus log to the base d of 1 over c. But c is less than 1 by the Kraft inequality, so 1 over c is greater than 1, and log of something greater than 1 is greater than or equal to 0. And now we're done. Therefore, L minus HD greater than or equal to 0. And we have some extra things. With equality, if and only if Kraft's inequality is satisfied with equality, and if and only if Pi equals Ri. But as I mentioned, the Ri's are of the form half, a fourth, an eighth, 16th, and so on. So the P, or there are only special distributions, P, the so-called d-adic distributions, for which you can have equality here. All right. So that's then. We have now not only shown that you want that you can't beat the entropy for any assignment satisfying the Kraft inequality, but that you can achieve it for the d-adic distributions P. And by the roof code argument, you can come within one of this. And so there you are. Now, let's look at the wrong code. Let x be drawn according to P of x. P is true. Probability mass function. It's the true probability mass function. You believe distribution is Q of x. In fact, you design your code as if Q of x is true. So, then L of x is equal to log 1 over Q of x is the ideal code word length with respect to WRT, with respect to Q. Notice, if Q is true, the summation Q log 1 over Q equals H of Q. In other words, we actually achieve the entropy lower bound by this. Why do I call it the ideal code word length? Well, it might not be an integer. If we keep track of the integer part, we could do it, but we lose track of what we're talking about. So let's not. Let's just assume that we can achieve the ideal code word length. It'll bring us down to H instead of sticking us between H and H plus 1. Okay, now. So L of x is the ideal code word length for Q. So suppose P is true, P is true, we have supposed it. Then the expected length of L of x, we just